Welcome to the lecture series on numerical methods, and currently we are discussing here numerical differentiation. So, basically we are just dealing here this numerical differentiation based on different interpolation formulas, like some of the finite difference operators, some of the like unequally spaced intervals. So, today we will just discuss about this numerical differentiation based on undetermined coefficients and some of these approximations using unequal intervals based on general formulas like Taylor series expansion. So, first we will just go for this differentiation using method of undetermined coefficients. Sometimes we may be interested either to devise a differentiation formula considering some of the specific ordinates. This means that if some of the specific ordinates are consisting of certain differentiation formulas or certain differentiation approximations it is asked to evaluate. So, how we can just do that one? Suppose a formula is written in the form like f dash of x 0 this equals to a f of x 0 plus b f of x 0 plus h plus c f of x 0 plus 2h here. Sorry, 3h suppose. So, how we can just determine this coefficients a, b, c from this derivative here. Specifically, if we want to determine this coefficients a, b, c, we have to expand this f of x 0 plus h and f of x 0 plus 3h by Taylor series expansion here about this point x equals to x 0. So, the basic idea is that sometimes if these nodal points are defined and if the functional values are given at that nodal points, so how we can just evaluate these derivatives at that point suppose. And here the hints is given that suppose your first order derivative is prescribed at a particular point, that is in the form of like f of x 0 plus b f of x 0 plus h plus c f of x 0 plus 3h here, and it is asked to like find these coefficients for this derivative formula here. So, if you just expand this Taylor series expansion of f of x 0 plus h at point x 0, then we can just write this Taylor series expansion as f of x 0 plus h f dash of x 0 plus h square by factorial 2 f double dash of x 0. So, likewise we can just write. Similarly, if you will just expand f of x 0 plus 3h here, this can be written as f of x 0 plus 3h f dash of x 0 plus 9h square by factorial 2 f double dash of x 0 plus all other terms. So, if you will just eliminate here the terms containing f double dash of x 0 from these two equations by suppose multiplying this first equation by 9 and subtracting the second from it. If you will just do that one, so if you will just see here, so we have to multiply here 9 and then if you will just subtract, this term will be just go out, and from there itself we can just evaluate f dash of x 0 in terms of f of x 0 and f of x 0 plus h and f of x 0 plus 3h and all other remaining terms, that is of higher powers of h containing f triple dash of x 0 and all other higher order derivatives there. So, if you will just multiply this equation 1 by suppose 9 and from the second equation if you will just subtract here, then we can just obtain f dash of x 0 as 9 f of x 1 minus 8 f of x 0 minus f of x 0 plus 3h here divided by, it can be written as 6h plus h square by 2 f triple dash of x 0 plus all other terms are there. So, if you will just consider this higher power terms as order of h here, then we can just write this expression as f of x 0 plus h minus 8 f of x 0 minus f of x 0 plus 3h divided by 6h plus order of h square here, or order of h you can just also write sometimes, since a higher powers of h can be neglected if h size is very small here. And if you will just consider this truncation error term here, so the truncation error term can also be written in the form like this equals to h square by 2 f triple dash of zeta, where zeta lies between x0 to x0 plus 3h. Obviously, in a compatible way, if you want to write, so we can just write this formula, that is in the form of like 9 f1 minus 8 f0 minus f3 divided by 6h, this equals to or approximates to f dash of x0 here. So, this above formula can also be obtained by equating these coefficients after expanding the function by Taylor series expansion also, sometimes we can do that one. But in this form, especially if you will just write here like 9 f1 minus 8 f0 minus f3 by 6h. So, we have to consider this h size should be small there. So, then this higher powers of h can be neglected. So, if you will just go for this other method of determining these coefficients, if you will just expand this one by Taylor series, if you will just see the first term a f of x0, we will just keep that one as a f0 here, and the second term we can just write this one in the Taylor series expansion form, and third term we can just write it in Taylor series expansion form. Then both sides we will just equate the coefficients, and if we will just solve these equations, then we can just find the values of a, b and c there. So, for that, if you will just rewrite this equation in the form as this one, this equals to a f0 here. So, then b of f of x0 plus h f dash of x0 plus h square by factorial 2 f double dash of x0 plus h cube by 3 factorial f triple dash of x0 plus all other terms. Similarly, plus c into f of x0 plus 3h f dash of x0 plus 9h square by factorial 2 f double dash of x0 plus all other terms. If you will just equate the first coefficient here like f0 coefficient, then right hand side we do not have any, or in the left hand side we do not have any coefficient for f0 there. So, that is why we can just write this coefficient as 0 if you will just consider only f0 coefficients from the right hand side there. So, first if you will just separate all these coefficients from the right hand side, then first one it can be written as a plus b plus c here into f0. Second one, if you will just see here, that is a b plus 3c h f dash of x0 plus h square by 2 factorial if you will just see here. So, that is a b coefficient it is just taking b plus 9c here into f double dash of x0 here plus remaining terms are there. So, if you will just equate this coefficients, so first coefficient we can just write a plus b plus c, this equals to 0 here. Next coefficient we can just write b plus 3c, this equals to 1 here, and immediate next coefficient if you will just write b plus 9c, this equals to 0 here. So, if you will just solve these 3 equations, since we have here 3 constants, so that is why if you will just solve these 3 equations, then we can just obtain that one, the solution as C equals to minus 1 by 6h and B as 3 by 2h and A is minus 4 by 3h here. If you will just put all these coefficients, then directly we can just obtain this formula for f dash of x0 as, since f dash of x0 that is written as A is minus 4 by 3h f0 plus B as here 3 by 2h f1 plus C as here minus 1 by 6h your f3. And if you just solve this equation, then we can just obtain this formula as 9f1 minus 8f0 minus f3 by 6h here. That is the basically that formula we have obtained in the earlier formulation also. Next we will just go for these derivatives that deals with like unequal intervals here. So already we have considered this approximation of derivatives when the function values were prescribed at equal intervals at the beginning. We have already discussed in the previous lectures, and in many practical problems usually we can just get that one, the function values are given at the nodal points which are not necessarily evenly spaced. And if we will not use any interpolation formula like Lagrangian interpolation or divided difference, Newton's divided difference interpolation formula, how we can just find this differentiation using directly this Taylor series expansion if we have unequal spaced points, that we will just discuss now. So if we will just go for that formulas, first if you will just discuss about like forward difference formula here. Let us suppose that the function values f of x are given at the abscissas like x equals to x0, x equals to x1 and x equals to x2 suppose. And if the space points are situated at h1 distance from x0, the first point, and second point if it is spaced at suppose x1 to x2, the space size is h2 here. So we can just write these 3 points, suppose the abscissas are prescribed at x equals to x0, x1 and x2 here, and the points are placed like starting point is x0 here, and at a point h1 distance suppose x1 is placed, and at a distance of h2 x2 is placed there. So if you will just write here in terms of x0, x1 can be written as x0 plus h1 here, and x2 can be written as x0 plus h1 plus h2. If you will just do the Taylor series expansion at f of x1 and f of x2 about x0 here, so then we can just write f of x1, this can be written as f of x0 plus h1 here, and that can be written as f of x0 plus h1 f dash of x0 plus h1 square by factorial 2 f double dash of x0 plus h1 q by factorial 3 f triple dash of x0 plus rest of the points. Similarly, if you will just write here f of x2 here, this can be written as f of x0 plus h1 plus h2 here. And obviously if you will just keep this one as in the form of h here like h1 plus h2, this can be written as f of x0 plus h1 plus h2 f dash of x0 here plus h1 plus h2 whole square divided by 2 factorial f double dash of x0. So likewise we can just write. And if you will just try to evaluate suppose f dash of x0 from these two equations. So from the first equation we can just write f dash of x0, this equals to f of x1. So this equation, if individually we try to evaluate f dash of x0, then we can just write this one as f of x1 minus f of x0 divided by h1 plus, if you will just see here 1 h1 it can be taken out, so minus h1 by 2 factorial f double dash x0. rest of the terms are there. And if we want to write that one in terms of error term here, then we can just replace this x0 point as zeta, where zeta should be lies between x0 to x1 here. And suppose if it is asked to obtain a higher order formula, so then we can just eliminate f double dash of x0 from this first two equations, like whatever we have just defined here, f of x1 and f of x2, from these two equations. So then we have to multiply, like first equation, if you will just multiply here h1 plus h2 whole square into the first equation, and second equation if you will just multiply h1 square. So then if you will just subtract these two equations, then we can just obtain the values of f dash of x0 in terms of f of x1, f of x2, f of x0, and the higher powers of h, or the higher powers of derivatives there. So if you will just multiply these two terms by eliminating f double dash of x0 from these two equations, then we can just obtain this derivative as f dash of x0, this equals to h1 plus h2 whole square, f1 minus h1 square, f2 minus h1 plus h2 whole square minus h1 square into f0 plus h1 into h1 plus h2 by 6 f triple dash zeta, that is as the error term there, and the first term whatever we have just written, that is divided by h1 h2 into h1 plus h2 here. And if you just see here, this error term contains only f triple dash zeta, since we have eliminated f double dash of zeta from this term here, where we are just given the symbols or denoted this f0 as f of x0 and f1 as f of x1, f2 as f of x2 there. And the second derivative, if you want to find from these two equations here, f from this equation like f of x1 and f of x2, so then we have to eliminate f dash of x1 from the equation, or f dash of x0 from that equation. So if you will just eliminate f dash of x0 by multiplying, suppose h1 plus h2 in the first equation, and second equation only h1 it can be multiplied, and both these equations, after this multiplication, if both these equations will be subtracted, then we can just obtain the second order derivative in terms of the f0, f1 and f2 there, where all the coefficients will involve in terms of h1 and h2 only, and higher powers of terms will be involved these derivatives of third order or higher powers, where f dash of x0 is just eliminated from these two equations. So if you will just go for this unequal spaced points and in a backward difference formula form, suppose the values of f of x are given like x0, x of minus 1 and x of minus 2, like our Newton's backward difference formula. So if you will just go for this backward difference formula here, we can just write these nodal points, that is in the form of x equals to x0, x of minus 1, x of minus 2. So usually we have to go back from x0 in a line. If you will just define x0 is the last point, like our Newton's backward difference formula. So the immediate previous point, it will be x of minus 1, it can be placed at h1 distance, and if you will just consider here x of minus 2 here, and which is placed at a distance of h2 from x of minus 1 here, then we can just write x of minus 1 as x0 minus h1 here, and x of minus 2 it can be written as x0 minus h1 minus h2 here. And then we can just use this Taylor series expansion at f of x of minus 1 there. So then we can just write f of x of minus 1 as f of x0 minus h1 here. And if you will just write in Taylor series expansion, that can be written in the form of f of x0 minus h1 f dash of x0 plus h1 square by factorial 2 f double dash of x0. So likewise we can just write, next term is minus here. So similarly, if you will just write this f of x of minus 2 here, then we can just write that one as f of x0 minus h1 minus h2. and it can be written as f of x0 minus h1 plus h2 f dash of x0 plus h1 plus h2 whole square by factorial 2 f double dash of x0 plus all other terms. So, if you want to find this derivative of f at point x0, so from the first equation we can just write that one as f of x0 minus f of x of minus 1 divided by h1, that is the first order derivative at x equals to x0, and the remainder term that will be represented in the form of h1 by 2 f double dash of zeta here, where zeta should be lies between like x0 to x of minus 1 here. Similarly, a higher order formula may be obtained by eliminating f double dash of x0 from the above equations by eliminating f dash of x0 from both these equations, f double dash of x0 from both these equations here. So, that is why if you want to eliminate f double dash of x0 from these two equations, then we have to multiply h1 plus h2 whole square in the first equation and h1 square in the second equation. If we will just multiply and subtract, then we can just obtain this formula for f dash of x0 here in terms of higher powers of h, and the remainder term especially it can come in the higher powers of higher derivative powers of f here. So, that is why this first remainder term it is just coming in the order of 3 here, and this remainder term is usually written as h1 plus h1 into h1 plus h2 by 6 f triple dash of zeta, where zeta should be lies between like x0 to x of minus 2 here. Since the points are existing between x0 to x of minus 1, so zeta should be lies between x0 to x of minus 1 here. Similarly, if we want to evaluate the second order derivative, then we have to eliminate the first order derivative term from both these equations. So, that is why we can just multiply in the first equation here h1 plus h2 and in the second equation only h1, and if you will just subtract, then we can just obtain this second order derivative in the form of h1 and h2 f0 f of minus 1 f of minus 2 here. Next we will just go for like central difference formulas. In the central difference formula, if you will just write these points, that is in the form of, we have like these points x0 is the center line. So, that is why we can just write x as x of minus 1 at the previous point. So, x0 is the center line here. So, that is why we can just write h1 as x1 here, and if you will just write like x of minus 1 here, that is h2 space here. At that point we can just use this Taylor series expansion as f of x of minus 1 as f of x0 minus h2. Similarly, at f of x1 we can just use f of x0 plus h1 here, and if you will just expand in Taylor series expansion at both these points, like at x equals to x0 there, then we can just obtain this Taylor series expansion at f of x of minus 1 and f of x1 there. To obtain this first derivative here, so if you will just eliminate f double dash of x0 from both these equations, then we can just obtain the derivative at, or first order derivative of f at x0 there. So, this first order derivative at x0 for f, it can be written as h2 square f1 minus h1 square f of minus 1 plus h2 square minus h1 square whole into f0 divided by h1 h2 into h1 plus h2 plus h1 h2 by 6 f triple dash of zeta, where zeta lies between x of minus 1 to x1 here, since this is a central difference formula here. And sometimes if you will just use, suppose h1 equals to h2, both spaces are equal, then your formula can be rewritten as f dash of x0 equals to f1 minus f of minus 1 by 2h. Usually this is the central difference formula for all other formulas also. This means that if you will just expand f of x plus h and f of x minus h, and if you will just add both these terms, the same formula you can just also obtain also. So, that is why this f dash of x0, it can be written in the form of f1 minus f of minus 1 by 2h, and this remainder term that can be written in the form of like h square by 6 f triple dash of zeta, where zeta should be lies between like x of minus 1 to x1 here. And if we will just go for second order derivatives here, second order derivative means we have to eliminate f dash term from both these equations there. So, if we want to eliminate both these equations of the terms of like f0 dash, then we have to multiply in the first equation h1 square by 2 factorial or h1 square if you will just multiply, in the second equation if you will just multiply h2 square, then we can just eliminate, sorry, if you will just multiply in the first equation like h1 and second equation like h2, then we can just eliminate f dash of x0 from both these equations, and we can just obtain this formula for second order derivative in central difference approximations. And this formula is can be written as 2 into h2 f1 minus h1 plus h2 f0 plus h f of minus 1 divided by h1 h2 whole into h1 plus h2, and the remainder term that will be represented in the form of like minus 1 by 6 h1 cube plus h2 cube by h1 plus h2 f fourth of zeta. Since third order term it will just associated with some of these constant terms here, that is why that cannot be neglected. So, that is why this one more term it will be associated like minus 1 by 6 h1 minus h2 f triple dash of x0 there. Since central difference approximation we are just approximating at these 2 points, like 3 points we are just considering for this one. And in this form also if you will just consider this h1 equals to h, h2 equals to h suppose, then we can just write f double dash of x0, it can be written as f1 minus 2 f0 plus f of minus 1 by h square, and this error it will just occur in the order of h square here, and that can be written as a minus h square by 6 f fourth of zeta, where zeta should be lies between minus x of minus 1 to x1 here. Thank you for listening the lecture.